All right, next up, I'd like to think about the problem we just solved geometrically, which sometimes helps you all connect more with what's actually happening and at least gets us thinking visually, which is important later in class. So our whole problem was that we had a function, f of xy equals 1 minus x squared minus y squared, which we plot as z equals 1 minus x squared minus y squared. So this red thing right here is the surface we cared about. And we cared about x and y greater than 0, so I'm just zooming in right here where x and y are positive. And if somebody asked you to maximize this function, you could say, okay, the highest it possibly is over here, and I guess if I have to have x and y positive, then down here is where it's the lowest. All these values right here have x and y positive, and z is 0. Actually, you could even go lower. You could say, okay, well, down here, x and y are really big, and z is very negative. So there's your maximum. Your minimums happen somewhere down here, depending on where you cut off your plot. But this section was a little different in that we had constraints. So we said, we also think that x plus y should be equal to 1. So that first red bowl was our function that we want to maximize or minimize. And this blue sheet that just appeared is our constraint, x plus y equal to 1. If I turn it down this way, this line should look just like this line right here I drew when I was trying to convince you what our constraint looks like in the xy plane. So what we're saying here is that we want to look at the biggest and smallest values of this red curve, but only where we live in this blue space, where x plus y equals 1. And so GeoGebra has this cool thing where we can intersect two surfaces. So there we go. I picked my two surfaces. I picked the red one and the blue one, and it showed me that this blue line right here is where the constraint surface, x plus y equals 1, is true and runs into my red surface. It tells me the different values of f of x, y that I hit along that. And when I look at this plot, it's very easy for me to see if I have to have positive x and positive y, then there's one place where my f is very small. There's one place where my f is very small. And the highest my f can possibly be is like there-ish. We might have to move that one. What I'm doing is I'm changing the points so that they show me what their value is. And that one we do have to move. So let's see if we can move it a little bit. There we go. Okay. So I'm just going to zoom in even closer here. Just by looking at this picture, I picked that my two lowest values are at points A and B. So A is the point where x is 1, y is 0, and z, or f, is 0. That matches this minimum we found right here. When x is 1 and y is 0, f of 1, 0 is 0. So that's that point. Point B is where I picked that. Oh, sorry, I'm so bad. I make this thing spin all the time. Okay. X was 0, y is 1, and f is 0 again. That's that other minimum we found when we're at the point 0, 1, x 0, y 1. We know that the value of f is 0. So those two bottom points tell us the minimums, and we can see we found those 2 points when we looked at the edges of our constraint. So for some reason, my axes have disappeared. There they go. So here's my constraint. Here's the edge of x equal to 0. That point is sitting right there on that edge. Here's the edge where y equals to 0. That point is sitting right on that edge. This point C was calculated the other way. What it is it's kind of like a turning point on the interior of our constraint. And it's at the point x equal to a half, y equal to half, z or f equal to a half. And that matches the maximum we found. X equal to a half, y equal to a half is the point, and the function evaluation is a half. So this didn't tell us anything new. I just thought maybe seeing it on a plot might help you understand what we're doing. We're taking a surface or a function or a thing that we care about, and we're chopping a part of it out. And we're looking for only where the special constraint is satisfied, which happens to be this line. And then we're just using calculus and algebra and all that stuff to find places where it's highest and lowest. I wanted to show that to you in GeoGebra because I think you're more comfortable using GeoGebra, so you could kind of like do this with your own problems. But CalPlot 3D has cool tools that I want to show you as well. So we're going to do this again where we struggle through using this tool. So here's the surface z equal to 1 minus x squared minus y squared. That's that red bowl shape that I started the GeoGebra plot with. And what order do I want to do this in? Okay, we're going to introduce the idea of the contour lines real quick. So I'm about to show our contours on the surface and on the XY plane. Just give it a second to think. Okay. So remember, these contours are showing us the level curves. So it's like if I take a horizontal slice right through it at different constant values of z. So here's where z equals to 3/4, a half, a fourth, and 0. And the gray lines down below are kind of projecting these level curves into the XY plane. You can also see that projection right here. There are these like quarter circles that are just taking these different level slices and smooshing them down into the XY plane to look at. We're going to need these later. We've used these before, so hopefully they're feeling kind of familiar to you. I'll leave it there for now, it's fine. Next, I want to plot my constraint. So that x plus y equals 1, I've plotted right here. It's that blue sheet we looked at. And here you can see kind of that shadow of the intersection where we actually looked for our maximum and minimum before. And you can see the maximum is right on this 0.5 level curve because the level of our maximum was f equal to 0.5. And I'm going to make this a little bit shorter for us. Did that work? Yeah, okay. So you can't see that intersection so well anymore, but what I actually want to be looking at is this projection up and down. Okay. Actually, what I'm going to do is I'm going to go back to my surface C, and I'm going to erase our surface for a little bit. I'm just going to hide it from us, and I also don't need contours on the surface. So this mesh that shows us our bowl shape is going to disappear, but the contours in the XY plane will stay. Okay, so all these gray lines, sorry, I'm just trying to organize this. It's really hard to use the rotate. I'm trying my best. Okay, I don't know how to pan over. That is a skill I don't have, so I'm just going to use this tiny corner of the screen right here. All right, so this line we're seeing is that top-down view of when our x plus y equals 1 gets smushed down into the xy plane. It's a line that starts at 1, goes to 1. Y equals 1 minus x. These gray lines are level curves. And when we're solving this constrained optimization problem, what we want to do, if we're finding the maximum, is we want to find places where this line intersects with the largest possible level curve it can find. That happens to be this one right here, the f equal to a half. The constraint intersects with this level curve right here there's some point where x plus y equals 1 and f is equal to a fourth, but that's not the highest it can possibly be. This point came out of our solution, grad f equals lambda grad g. And what's happening is, I'm going to say this and you might not believe me, but if I know my constraint is going to intersect with my level curves, and I want to find the biggest level curve it can possibly intersect with, you imagine that there's a bunch of these quarter circles all the way through this space. But the largest one it can possibly touch is going to happen when the constraint is exactly tangent to that level curve. See how right here at the point a half, the constraint is tangent to this quarter circle level curve? That happens every time we're looking at one of these constrained optimization solutions. That's not a coincidence. And so when we solve that grad f equals lambda grad g, what we've done is we've created a little algebra problem for us. As long as we include that g equals c that says we're on this line, then solving grad f equal lambda grad g says find the point where that line is tangent to the level curves of f. And remember, the level curves of f are related to the gradient in a special way. That's why gradients end up involved in this equation we solve. It's okay if you don't understand like that reasoning. I'm never going to expect you to derive this formula. It's enough to remember it. But I'm hoping that looking at enough pictures like this will help you see exactly what you're